Hello and welcome to the series of instructional videos for the third year Analytical Chem Labs. I'm Dr. Robin Studley, and this video will be about the instrumental setup for atomic absorption spectrophotometry. The instrument we're looking at is the PerkinElmer 305A Atomic Absorption Spectrophotometer. What we see today will be very typical of a double beam atomic absorption system. First, let's look at the light source. The source in this instrument is a hollow cathode lamp, or HCl, which is a source of highly monochromatic light. Each lamp is specific to a certain metal, so if you're analyzing more than one metal, different HCLs are required, and only one HCl can be used at a time. When a voltage is applied to the HCl, the inert gas inside is ionized. These ions then accelerate into the metal cathode, sputtering atoms from the cathode. The sputtered atoms then collide with other particles or atoms, leading to electronic excitation. The excited atoms emit photons as they return to the ground electronic state. The photons travel through the quartz window and are reflected towards a rotating chopper. The chopper has two halves, one that is open and the other is a mirror. The chopper rotates rapidly when in use. When the chopper is in the open position, the light beam is passed through towards the monochromator. This is the reference beam. If the chopper is in the mirrored position, the light is reflected into the sample compartment. This is the sample beam. The double beam setup helps to account for fluctuations in lamp intensity. At the two different chopper positions, two different signals are measured. This is due to the fact that at the open position, the light beam does not pass through the sample holder, leading to no absorbance. However, when the light beam passes through the sample holder, the analyte is absorbing light. Thus, as the chopper rotates, the measured intensity oscillates between a high and low level. The sample is introduced into the instrument through the capillary. In the nebulizer, the sample is mixed with a fast-moving flow of air and fuel to create an aerosol. Flow spoilers, or baffles, in the nebulizer ensure complete mixing and act to remove larger droplets. In the sample compartment, the flame itself acts as the cuvette. An air-acetylene flame is used in this experiment. In the flame, there are three different regions: the primary combustion zone, the interzonal region, and the secondary combustion zone. The best region of the flame for analysis varies with analyte, since the temperature of the three regions are different. This causes different interferences to become more or less prevalent. The droplets that make it to the flame become desolvated and atomized due to the high temperature, which is about 2200 degrees Celsius. These atoms absorb some of the light passing through the flame, resulting in a decreased amount of light transmitted when sample is present. The light transmitted through the flame passes through a patterned mirror and is reflected towards the monochromator. Similarly, the reference beam is reflected towards the monochromator. The photons enter the monochromator through a slit and are then reflected onto the diffraction grating. The grating causes spatial separation of wavelengths. The dispersed light is reflected off the grating to another mirror and is directed through the exit slit to the detector, which is a photomultiplier tube, or PMT. In the PMT, the photons strike the photocathode, causing electrons to be emitted. To amplify the signal, the electrons are accelerated towards 9 consecutive dinodes, where a cascading effect of the electron emission occurs. The signal from the PMT is converted into an electronic signal, which leads to an absorbance reading. I hope this video has been useful for you. If you have any questions, please direct them to me or your TA, and thanks for watching.